Video 4 is a continuation on video 3. I guess they're all continuations, but it's just a little bit more with Lewis structures. So, on the previous one we did 4 Lewis structures that followed the basic steps and basic rules, where we made sure everything had an octet, we made double or triple bonds only if we needed to, and I didn't really point this out, but you don't start with double bonds and triple bonds. Because these atoms want more electrons, and once again the want meaning because they attract more electrons because of the high electronegativities, each element ideally would have a complete octet on its own without needing to share. So the only reason it shares is it can't complete its octet without getting it from somewhere else. So if possible, it wants to have as many of its own electrons that don't belong to or are not a part of another atom's octet. That was maybe a confusing way of saying whenever possible, the atoms want to be single bonded. If they can't be single bonded, they'll be double bonded. If and only if they can't be double bonded, then they'll have a triple bond. But you don't start with that because we have to use all of our electrons, and we also need to make sure each atom has as many of its own electrons as possible, which we'll explain in one of the next videos with formal charge. But the octet rule is kind of a general guideline for how to make these. And it applies in most compounds, and even though this is AP and it's a little bit harder, it will apply still to most of the examples that you see. But AP is about exceptions. Do you know the chemistry plus the weirdness? We did some of these exceptions in first year, so these aren't crazy things that you've never seen or never heard of, but we just want to understand more about them. So there are 3 ways we could have exceptions to the octet rule. We could have a compound that has an odd number of electrons, a compound in which one of the atoms is stable with fewer than 8 electrons, or a compound in which an atom is stable with more than 8. This exception right here, as it says, is the most common of these 3. This will definitely come up. The others may or may not come up. And we're going to talk about them as we do our examples. So A is NO, and that looks a lot like example C from the previous, except it's not NO+. So NO is nitrogen and oxygen, 5 electrons, 5 valence from nitrogen, 6 valence from oxygen for 11 electrons in our drawing. And just the fact that that number's an 11 and we're always pairing things up and putting things in sets of 2, the 11 should make you feel a little bit uncomfortable because it means we've got an odd number and I can't put pairs of dots around this that'll work. So this is exception number 1. If the number of electrons is odd, which it is, we can't get everything to have 8. But that doesn't mean that we don't try to get close. We get as close as possible to each thing having 8 electrons without breaking any of the other rules. So if I put all my dots in 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, I've got 12 dots in a line. I've got 14 electrons here, so that's way too many. So as I get rid of some of these right here and change that from 2 sets of dots to a line, and now I have 2 4 dots on nitrogen, 2 4 dots on oxygen, and 2 4 electrons being involved in the bond, I'm still using 12 electrons. I only have 11. If I did this, erasing those electrons and making it a triple bond, I have the drawing I have from before. I have 6 electrons involved in the bonds, 2 on nitrogen, 2 on oxygen for 10, but I don't have 10 electrons. I have 11. So if I put another dot there to make 11, it doesn't work. In doing that, nitrogen has 6 electrons from the bonds and 1, 2, 3, which is too many electrons. That is 9 electrons. if I put the extra dot here. The oxygen has 6 electrons in the bond, and 1, 2, 3. That's too many. That's 9 electrons. If I go back to this drawing, that has 12 in it. And hopefully you can count those, 4, 4, and 4. The other drawing only had 10. So I kind of have to be in between there. So what's going to happen is I'm going to erase just one of those. So now I've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. That's using the correct number. Oxygen has a set of 8, so the oxygen is stable, but the nitrogen only has a set of 7. This is the best Lewis structure for this. This is the closest thing that we can do to everything having an octet without going over. And the reason I took the electron from nitrogen instead of from oxygen in that, and we'll prove this later with a concept called formal charge, but the idea is oxygen is more electronegative. It wants electrons or attracts electrons more properly better than nitrogen does, so it's more likely to complete its octet than nitrogen is. So that's an odd number. It doesn't happen a lot, but it'll happen every now and then, especially when you have a nitrogen compound, sometimes something with a halogen, something that has 5 or 7 of its own valence electrons. There we go, that's all cleaned up. So now we have PCl5. We have a phosphorus with 5 valence electrons. We have 5 chlorines, each of which have 7. So we have a total of 40 electrons here. But as I connect this, I've got phosphorus to chlorine, to chlorine, to chlorine, to chlorine, to chlorine, and just by connecting that, I'm violating octet rule. Phosphorus has 5 electrons around it, or 5 sets, 5 pairs of electrons. But this is okay because phosphorus is in period 3. That means row 3 on the periodic table, and it's a large enough atom that in some compounds it can hold more than 8 electrons. This can't happen with everything. We said it wasn't possible with the nitrogen, it wasn't possible with the oxygen to have 9, but here the phosphorus can have 10 because of the larger radius of the atom, it can accommodate more electrons. It doesn't happen a lot. It most commonly happens when it's bonded to something that's very electronegative, oxygen, fluorine, or chlorine. So we've got phosphorus bonded to all of these. So even though we've broken the octet rule, we still want to follow the other basic rules and fill everything up. And when we fill everything like that, we've got 8, 16, 24, 32, 40 electrons. Chlorine has 8, 8, 8, 8, 8. Those all have good octets. And phosphorus has at least 8. It has a set of 10. So this can happen with phosphorus, with sulfur, with elements in periods 3, 4, 5, 6, and 7. The larger atom with the higher number of protons can attract and have more electrons. There's some theories, and you may read about this, you may hear about this, about the available d orbitals. There are some studies that support that as how this is happening. There's some that don't. So that's not really the conclusive explanation at this point. But it's just once your atom's big enough, in certain circumstances, it can hold more than 8 electrons. But it has to be in row 3 or below. So this is a good example of that with phosphorus. Our next one's boron trifluoride. And as we add this up, boron has 3 valence electrons. The fluorine has 21, so we've got a total of 24. And this I know is an exception, so I am going to jump right to what it would end as. So we do all of this, we put all of our dots, and normally then we would check, Have we used enough? Do we need to move them, make doubles, triples, etc.? Well, we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Fluorine has 8, fluorine has 8, fluorine has 8, but boron only has 2, 4, 6. But this is a new exception. Boron, when it's the central atom, forms stable or at least relatively stable compounds with only 6 electrons around it or 3 single bonds. So technically I could take these electrons right here and shift them over and make a double bond, but experimental evidence proves that that's not what happens. We don't move those electrons over to make this a double bond because that's not what happens in this compound. There's a reaction of ammonia and boron trifluoride that shows how these electrons are shared and proves that boron doesn't have those 2 electrons there. So with boron, and boron is the only major exception to this, it is most stable, or at least most likely, that it forms 3 single bonds, even if it were possible to draw a Lewis structure where double bonds could give everything an octet. And once again, I keep alluding to this, I keep talking about it coming up. Formal charge helps us to prove that. So the last one here, as we look at it, it doesn't necessarily look like any sort of exception, but we're going to add it up. Sulfur's got 6 valence electrons. There's fluorines, each one has 4, or excuse me, each one has 7. There's 4 of them, so 28. We've got 34 electrons. Sulfur goes in the center. Seems like it should be a piece of cake. 4 bonds, use our electrons, fill our octets, and move on. And I'm saying all of that it seems like it should be easy. So you're probably knowing that it's not going to be quite that simple. But we draw it, and we've got 8 electrons, 16 electrons, 24 electrons, 32 electrons. Well, I need to use 34. But as you look at this, you'd think, well, fluorine has 8, and 8, and 8, and 8. Those are all stable. Sulfur has 2, 4, 6, 8. It's stable. What am I going to do? Fluorine is in period 2. It can't hold any more electrons. It is stable as is. Sulfur is in period 3. It is stable, or can form stable compounds with 8 electrons, but it is our most common exception here. It can have more than 8. So I'm going to put that last pair right there. So you have to have that. You have to use all 34 electrons. You can't just say everything has an octet, it's close enough, I'll call it good. You got to make sure that your drawing represents the electrons that are available to you. So that one doesn't pop off the page as an exception. So if you had a multiple choice question, which of these is or isn't an exception, it'd be easy to see, okay, the PCl5 means that there has to be 5 things bonded to it. That's 10 electrons, that's an exception. But SF4 doesn't seem as obvious in terms of that. Not sure why that was still there. But then we look at this last thing. There is one term that kind of comes along with some of these things that I just want you to be familiar with and have heard. We can form a special kind of covalent bond. It's not necessarily a single, double, or triple, but it's a bond. It's how the bond forms. It's a coordinate covalent bond. So when we form a covalent bond, we normally think of each atom contributing some electrons and them sharing those electrons. But sometimes the shared electrons used to belong to just one of the atoms. So here we have an oxygen molecule where we've got O2. Each one, after sharing its 6 electrons, is able to get up to 8 with the double bond. And this is an example of what I was showing you, that you can use dots to represent a bond. I don't think it looks as nice or as clean as if they were lines. So I could connect those, and I'll zoom in so it doesn't look too horrible. Come on, zoom in. So I could connect those, and then we'll come over here and look at the example of the coordinate covalent bond. So if I made these dots, let's see, there we go. there in a line, that's showing that's a double bond. I know it's not that much difference, but that's what those 4 dots mean when they're between the 2 atoms. So I've got O2, it's double bonded there. Well, this oxygen has 6 electrons. It needs 2 more. Right here, this has 8. So when this one sneaks in and starts sharing those electrons, those 2 electrons used to belong only to this atom. So this atom right here isn't sharing any of its own. It is sharing, but it's sharing electrons that previously belonged only to another atom. That's a coordinate covalent bond. By looking at a bond or by looking at a completed Lewis structure, you can't necessarily identify something as coordinate covalent, but it does affect sometimes the polarity of the molecule. Very often or almost always the formal charges. Sometimes it plays into resonance and some other things we're going to see, but it also ties back to something we learned before. It is a Lewis acid-base reaction, and since we're doing Lewis structures, it's good to bring that same name up for a different reason. Lewis acid bases are electron pair donors, electron pair acceptors. Here we have something that's got that extra electron pair that it's donating to the bond. So that's mostly a vocabulary term that could pop up, and drawing Lewis structures can sometimes help you identify those, but it's not really too key or vital, just something you don't want to be surprised by if it's a part of the question. So from here, what we're doing is understanding and applying Lewis structures in lots of different ways. So make sure you understand these 2 videos and you have these skills down really well, because they're going to get you lots of multiple choice and lots of free response points.